All right. We're going to talk about how we are using Java at Netflix. And this is, as you can see, the 2026 edition. I've done this talk before, but every year is different because Java evolves, Netflix evolves. And that means there's a lot of new stuff to talk about. So let's go dive into it. Okay, so last year at this conference, about exactly a year ago, I was actually on stage during the keynote, and I kind of talked a little bit about how we are using Netflix, or Java at Netflix. And I basically said everything we built is on Java. And that is pretty much exactly true, but we will get to the details of that. However, people on Twitter got really upset. And apparently, we lost a whole bunch of people watching Netflix because you obviously don't want to watch something built on Java. It's too slow, it is not Rust, it is many things. Anyway, this is a Java conference, so I hope that we get a little bit more positivity here from you all. But we're going to really look at how we're using Netflix, where we're using Java at Netflix, and maybe we're not, and why we're doing these things. My name is Paul. I'm at Java Platform at Netflix. I've been at Netflix for 9 years now. I'm also the author of the DGS framework, which is the GraphQL framework that Netflix open sourced a few years ago. We'll talk a little bit about that. And in a long past ago, I wrote some books about Java modularity as well. Okay, we're going to talk about a whole bunch of different things. First off, we start talking a little bit about the Netflix architecture. That's actually quite similar to what I talked about last year, if you were here. And then we start diving into our Java stack, like how we're actually building these things. We talk about Spring Boot Netflix and kind of the different things we do there. We'll talk quite a bit about version migrations, because that is really important if you use open source frameworks like Spring Boot. We'll talk about JDK features and how we are adopting a lot of the new features that we're getting out of the JDK and the JVM. And finally, I want to spend a little bit of time on GenAI, because, well, how can I not talk about GenAI? And I really want to give a Java angle there and kind of show how we're bringing GenAI to our Java services as well. Okay, first we need to understand where we're using Java before we are talking about how we're using Java. Hopefully all of you are familiar with this screen. This is kind of the home screen of Netflix. This is where you pick your shows. If you have never seen this screen, well, we can talk later. But let's talk a little bit about like how this is actually implemented. So this is just kind of one part of Netflix, and that is what we call Netflix streaming. Of course, Netflix streaming serves millions of users across the world. It means that we get a lot of requests per second to deal with the backends that sit behind this. It's multi-region because we want low latency around the world, and we need to think about failover. And that really kind of defines the way how these Java services are built, how this microservices ecosystem is built. On the other hand, we have many Java applications that are more traditional enterprise apps. Like there's a UI, there's data, and the backend basically sits between the data and the user interfaces. These applications might be a little bit more typical and to some extent maybe a little bit more boring from a technical perspective, because they don't have that many requests, they don't have that many users. Often they can just be single region, we can use relational data stores. But this is also like a really big part of our business, because Netflix is also one of the largest movie studios in the world, and it means that we build a lot of software to help with those processes. So a lot of what we do is actually also just this more like boring stuff, but super important. And of course, the characteristics of these apps are very different from this super high performance, super high user kind of work that we do on the streaming side. Interestingly enough, the architecture for both of these types of applications is exactly the same. Let's take streaming. We have like the Netflix app running on your TV or your phone or your laptop, wherever you want to run it. And whenever you're browsing that home screen, we are making requests to a federated GraphQL service. So we're using federated GraphQL, and that means that every request is basically a giant GraphQL query that goes to this gateway. And in this gateway, based on the federation spec, we will basically see, okay, this part of the query can be handled by this microservice, this other part of the query needs to go to another microservice, and that is where the first fan out happens to these different backend GraphQL services. These GraphQL services, we call them DGSs, domain graph service, but it's really just a Java microservice that does GraphQL. Especially for streaming, very often from those first level DGSs, we then fan out to even more backend services that are responsible for very specific parts of that request. And you can, I kind of made up all these different boxes, but you can get a top 10 service, for example, which is just responsible for that part of the larger request handling. So what we see here is that first of all these services are built on Java, right? The backend services are running Spring Boot. They have a gRPC API typically. The DGS services, the GraphQL services, are all built on Spring Boot. The federated gateway itself is on Spring Boot. So all these backend pieces are all running on Spring Boot and obviously on Java. Now, if you really look at how Netflix actually works, this is only half of the story. So if I'm browsing to find my next show, that's kind of the architecture that we just talked about. That is what we call discovery. You're discovering your next show. The moment I actually click play on one of the shows, we actually go to a completely different code path, and that is all part of OpenConnect. And OpenConnect is basically, we have physical hardware in internet provider racks, and that is where the actual video bits are streamed from. And we do that so that when you're actually streaming video, those video bits come from a location close to your house, which saves, it saves you latency, it saves the internet providers a lot of bandwidth, which means they save a lot of money, and it saves us, Netflix, a lot of money as well, because we also don't have to pay for this bandwidth. All the management software for OpenConnect is also all built on Java. So on the one hand, it's like a Linux-based stack with custom hardware and things like that, but the actual management software is all Java and Spring Boot. And then there's a whole bunch of other Java-based things. We have encoding pipelines, we have stream processing with things like Spark, etc. We have a whole bunch of data stores actually built on top of Java. So these things are no longer Spring Boot, but it's all still running on Java. Well, the first thing you can now ask is, okay, why pick Java? There's so many other languages to pick from. Why not Rust? Seems Rust is getting pretty popular. People are excited about it. You get high performance and things like that. But there's always trade-offs. And to me and to us, Java is the best trade-off between runtime performance, developer productivity, and maintainability. It's good at all these things. Now, compare this to another language. Compare it to Python, for example. Python has really good developer productivity. It's really easy to get started. It's really easy to build your scripts. You don't need a lot of build tooling and things like that. But now you're suffering on runtime performance because things just run slower. And likely also on maintainability because an untyped language. Compared to C or C++ or Rust. Okay, now you can run really fast. Not necessarily faster than Java though. If you were just in a garbage collection or the memory management talk, maybe you have now a better understanding why Java can actually be faster than a language like C or C++. However, Java will be just as good as those languages from a runtime performance, but we get, of course, much better developer productivity and maintainability for our source code. So it's kind of this sweet spot of where it's good at all these different things, and there's really not any other language that has these qualities in the same way. So Java just works really well for these kind of applications that we're building. Now, is it all Java? Well, it depends how you look at it. Of course, the user interfaces that we run the Netflix application on, that's not Java. The application that runs on your TV is on a very optimized version of JavaScript, because that is what we can actually run on a TV. If you have an Android phone, of course, we're using, well, it's kind of Java, but not really. It's Android. On iOS devices, we use the languages fit for that. So for UIs, we use the language best fit for the device that you're on. And in all of those cases, that is not Java. We have some stuff in things like Go for like really low-level, platform-level things. Sometimes it just fits better into the ecosystem around Kubernetes, etc. But these are really, really tiny pieces for the most part. And then we have a lot of data science-related things and machine learning, and that is actually done in Python. And Python is just really convenient for these cases. And again, the trade-offs are different there, and Python is a really good choice there. For all our backend work, all our microservices, that is all Java. So I think we can fairly say that Netflix is actually powered by Java. When I say Java, I actually mostly mean JVM. So most of our services are all built in the Java language as well, but there's also quite a bit of Kotlin going on. It's kind of the same thing to me. It runs on a JVM. It has really good interoperability. So I kind of call it Java as well. But primarily, everything is in the Java language as well. OK, we have seen where Java is being used, which is pretty much everywhere in the backend. Now we're going to talk about how we're using Java. And first off, we're going to talk about the use of Spring Boot. So Spring Boot is basically our standardized developer platform. And at Netflix, we talk a lot about a paved road. And this is basically a set of standards that we pick with standard tools, frameworks, and libraries to make it really easy for developers to get started and to integrate with the Netflix ecosystem. Because we have to integrate with all our different services and security and things like that. And you all should get it out of the box. But it also makes it just easier to roll out changes and do things from a platform perspective. Because we have many, many teams. And, well, we already talked about how Java is used everywhere in the backend. But we have about between 3,000 or 4,000 Java applications, depending on what you count or not. So that's quite a bit. And all these things are standardized on Spring Boot. And we take basically Spring Boot for open source, and we pick basically the latest version and try really hard to stay really close to the latest open source version. We'll talk about that a little bit more soon. And on top of that, we build all sorts of different modules to integrate with the rest of the Netflix ecosystem. For example, we have our own security systems at Netflix to do authorization and authentication. Spring Boot, based on Spring Security, integrate with these systems, completely out of the box. So as a developer, you don't have to think about that. We have dynamic configuration, so we integrate with that. From a Spring developer perspective, you just have your properties, as in any Spring application, but actually there's a complex system sitting behind that. We have support for gRPC built into Spring Boot. We have support for other IPC clients as well, for like HTTP clients that take care of observability and security and all these things. Talking about observability, most of the observability systems that we use at Netflix are all custom built because there's really nothing on the market that works at our scale. So distributed logging and tracing and metrics is all in-house systems. And that means that our application stack, our Java stack, needs to integrate with that. And again, you get it all out of the box with Spring Boot Netflix. And then, kind of the same way as Spring Boot delivers their features through feature starters, where you basically have a dependency that you add to your build file when you want to have one of those modules. And we kind of structure that the same way internally as well. Now, the way we implement these different things is also the same way as how Spring Boot itself is built. If you're familiar with Spring Boot, pretty much all the components are delivered via auto configuration. And we provide our own components through auto configuration, either to add extra functionality or to override beans coming from open source out of the box and like customize it with our own behavior. And again, that means as a developer using Spring Boot Netflix, it all kind of looks and feels just like Spring Boot, like everyone else is using, but you actually get all this extra functionality out of the box. For configuration, we use environment post processors. Again, same mechanism as what Spring uses. And then for more complex features, such as gRPC Spring Client to integrate with gRPC, we have some Bean Factory processors, but that's really not even that much. And for all the components and all the functionality that we also provide test slices so that we can do testing specifically for these parts of the framework. And I have an example of that very soon, actually right now. So most of our tests that we write for our applications are all Spring Boot tests. And we also use the @Spring Boot test annotation. Now you might be wondering, why do this instead of using something like JDBC test or JPA test or WebMVC test? Well, the problem with these more like specific annotations that Spring offers is that you can only like focus on one layer of your application if you use those. And often that is not exactly how we want to test. Very often we actually test all the way from, for example, the GraphQL layer to the database layer, but only focused on one component. So we hit all the different layers, but only on one part of the functionality in a service. And we can really only do that with the more generic Spring Boot test annotation. Now the problem, of course, is if you use that completely out of the box, you will basically start up your whole Spring application for every test that you run, and that gets really slow. So what we always want to do is specify specifically the classes that we actually want to test. So these are the only components that we bootstrap, and then we add test slices, such as on this slide, enable DGS test or enable SSO test, that will then bootstrap just a small part of the framework just with the functionality that we need for this test, so that we get this really nice balance of tests that are really powerful. We can test like real things, but they're still really fast, instead of bootstrapping the whole application. Now, there's a lot more to talk about when it comes to testing, and I actually had a talk, I think 2 years ago, on Spring 1, which is recorded on YouTube, all about how we do our testing with Spring Boot. Now, of course, if you build on top of a open source framework, that open source framework, including Spring Boot, is going to move from version to version to version. And now it becomes a question, how do we move all our services from these different major versions? Because the chances between these major versions can be pretty significant. Now, the first time that we had to deal with this was going from Spring Boot 2 to Spring Boot 3. And the biggest change in that version upgrade was the change in the package namespacing from JavaX to Jakarta. But all of open source basically had to go from JavaX to Jakarta for all the specifications like the servlet spec and the JPA spec. And Spring Boot in version 3 decided, okay, we are going to adopt this new package namespacing. Now, if you're just an application and you, as like in your application code, are using JavaX, all you needed to do was basically a search replace from JavaX to Jakarta, and everything just works. But now throw libraries in the mix, and a library might be using javax.servlet. Okay, how can we upgrade this library so that it's compatible with Spring 3 or Spring Boot 3, while also still being compatible with Spring Boot 2? Because we will be in this mixed world where some applications are already upgraded, some others are not. So basically, we have this chicken and egg problem with libraries, that applications can't upgrade until the library upgrades, but the library can't upgrade until all applications are upgraded. So you're stuck. What we did specifically for this upgrade is we built a Gradle transform that does bytecode manipulation on artifact resolution. So when you download a library, it will basically rewrite the bytecode so that it will now use the Jakarta namespacing instead of JavaX. This only works for this specific change, because In this case, only the package name, the package naming changed. The implementation was exactly the same, so you can just safely swap one out for the other. So this doesn't work for every other major change. It only works for this change. But if you're still stuck on Spring Boot 2, we've actually open sourced this Gradle plugin, and you can use that and kind of get yourself unstuck. For other code changes, like API changes, we used a mix of Open Rewrite and Gradle lint for like the changes to our build files and actually the source code. And by combining all these different techniques, we could automate most of the upgrade work from Spring Boot 2 to Spring Boot 3. I say most because we still needed a person to actually run this tooling and maybe take care of some smaller things. There's always corner cases that we can't catch with this kind of tooling. But we have been running this for, I think, like 2 years now, and we're now finally completely on Spring Boot 3. Just in time to start worrying about Spring Boot 4. And you kind of see how this is always a problem, right? If you have a large organization with thousands of services, or maybe even smaller, you're constantly chasing like what's happening around you, right? We're constantly chasing new Java versions, we're constantly chasing new Spring Boot versions, we're constantly chasing all the libraries that we rely on. For Spring Boot 4, we have decided to actually completely drive this migration through Cloud Code. Now, what we don't want to do is tell every developer to, hey, why don't you go upgrade your service, run Cloud Code, and have fun with it? Because obviously, that would just waste a lot of people's time. So we want to use Cloud Code because it's very useful for doing this kind of work, but we want to run it headless as a batch job, so that we as platform can take care of upgrading all the applications that we have at Netflix. So we basically built a workflow engine on top of Cloud Code where every step in the upgrade is a separate prompt, it runs on a separate sub-agent. And that way we have like smaller changes that happen sort of in its own context. And we run all these things together. And finally, you should end up with a fully migrated Spring Boot app. The other thing that we did is we implemented a checkpointing mechanism where if something goes wrong during the process, of course you get like the Git status of where the project ended up, but we also get a full history basically of the conversation that Claude iterated through, so that we can basically, as a person, can start looking at a project that failed and get the exact state of both Claude and the source code itself, where it started failing, or when we need to inspect it for corner cases that we missed. We just started rolling this out, so I can't quite claim a success story yet, maybe next year, hopefully. But this does look really promising, and if this really works, and it definitely looks like it will work, this is something that we are going to use for basically all big version upgrades of libraries, frameworks, JDK versions, because it gives a lot more flexibility for us as platform to basically drive these changes throughout the whole ecosystem of microservices. So this is going to be kind of a big thing that we're going to see. Now you could be wondering, why upgrade at all? Things worked perfectly fine before Spring Boot, they worked perfectly fine on Spring Boot 2. Why do you keep chasing these versions? Because that, well, it keeps my team very busy at the very least. So why keep chasing open source? Well, this is basically because the world around us with open source and with the Java versions is continuously going to change, right? Maybe if you get a next Spring Boot version and you look at it and you look at the new features, there's nothing there that you're like super excited about. So you might be thinking, well, I can just as well just stick on the old thing. Now what's happening there is that all other libraries around Spring Boot are also going to change. And if you stay behind, sooner or later you're going to realize that, oh, I want to use this one new feature of this particular library, but I can't because Spring Boot, the version that I'm on, this old version, is not compatible with this new version of this other library, this new version of JPA, or this new version of Jackson, or Spring AI. So if we don't take care of like staying with the latest, basically, eventually we're going to get ourselves stuck, and we can't use the new features that we do really need to move forward. And we stop having the ability to innovate and to move fast. And that is why we kind of have the rule of thumb that when a change is external, so when things in open source for the libraries and the frameworks that we really care about, if they change, it is going to be eventually unavoidable. We can't hide this problem, we have to also move forward. And that means that we are going to prefer just ripping off that band-aid and taking care of this change, instead of only going to address the problem when it becomes a bigger problem and now it's much harder to deal with. Because going from, let's say, Spring Boot 2 to Spring Boot 4 or 5 or 6 or whatever, whenever we need to do this, would be much harder than to do one version upgrade. So it's better to do them sooner, but it also means that we have to do it more often. And that is really the thing that we try to focus on at Netflix in the platform org, is that we want to make it as painless as possible for the rest of the teams to basically adopt these new versions. And that means that we build upgrade tooling and that we can roll out these things without involvement of each and every developer. All right, moving on from upgrades, talk a little bit about GraphQL. So when we looked at the architecture, I mentioned that all this stuff is built on a GraphQL architecture, on a federated GraphQL architecture. And GraphQL works really well for us because it gives us a schema, which makes it really a lot easier to collaborate between like front-end developers and back-end developers, because you have that schema. And GraphQL gives you a very flexible schema, because it basically defines what data is available, and each client of that data can decide what data they actually need and just run a query giving the data that they would rely on. And on top of that, we have GraphQL Federation, which basically makes it possible to have that giant GraphQL schema with all the possible data in there, while the implementation is actually a microservices ecosystem where each service can be responsible for a really small part of that large schema. And when we think about GraphQL, you should think in data, not in methods. So it's not about calling a method on another service. No, it's about the data that is available from that service. Now, on the other side of things, if we do server-to-server communication, where you don't really care about this really flexible data, because, well, you mostly just want the same thing every time, but you do really care about like the highest performance you can get, we use gRPC. That is a super efficient protocol, and there we think about methods. I'm calling a method on another service, and not so much about data. So we have two different mechanisms for these two different types of use cases. Now, what does it mean for REST, that a lot of stuff is built on in the past? Well, it kind of means that we don't need REST anymore, because in pretty much every case, either GraphQL or gRPC would be the better mechanism. That doesn't mean that we can't use REST. If you have a very simple use case and you just want to make some data available really quickly, fine, use REST. But for anything that should remain for longer and that actually needs a good API, we basically don't use REST at all. Now, looking at the DGS framework, this is the framework that we open sourced a few years ago. You basically have your GraphQL schema and you implement the data fetchers for that GraphQL schema using annotations. So this fits really well in how you do programming in Spring Boot in general. And then the other really nice thing here is that we have a testing framework where we can basically bootstrap just the DGS framework in a test. And that allows you to run GraphQL queries through exactly the same framework stack as you would do in production, but these tests run really fast. So you don't actually bootstrap your whole Spring application here. This is a test that can run in like a second or so. All right, so we've talked about kind of our application stack. Now we go one level lower and we talk about the JDK and the new features that we that we get there. Now, first off, this is kind of super old news. When we moved from Java 8 to Java 17, we saw a lot better CPU usage because the garbage collector, the G1 garbage collector, just got a lot better. So no work or no tuning necessary. This is just something you completely get for free. But as I said, this is old news because for the most part we are not in Java, or actually we are completely not in Java 8 anymore. We have moved on to, at a minimum, 17 and in most cases 21 or 25. And when 21 came out, we started experimenting with generational ZGZ as a garbage collector. Now, our expectation was that generational ZGZ would be better for some very specific use cases. We didn't expect that this would be a good story for all workloads. And the reason for that is that, well, with ZGZ, you are basically giving up more CPU, so you spend more CPU time to get lower pass times on garbage collection. So lower pass times is good, higher CPU is bad. And we thought, well, that trade-off is probably not going to work for most of our services, but we tried it anyway. Now, what we started seeing is that actually it was really good for almost all of our workloads, and that's why we now actually made it the default. And the reason for that is that with the G1 garbage collector that we used previously, because we have pretty large machines with a lot of memory, at some point you're going to do a pass the world garbage collection event. And if you have a lot of memory, that can actually take quite a long time. And we were seeing pass times of about 1.5 seconds. Now, that's not that long. However, to keep the low latency that we need for the Netflix app, we have really aggressive timeouts on all the IPC calls that we do to these services. And it means that if you pause for a second, all the requests that go to that service will actually fail because they all time out. And it means now we have to retry all those requests. And that means more load on other nodes in the cluster. As a user of Netflix, you would probably not notice this. That's the whole reason that we have these super aggressive timeouts. But we are spending a whole bunch of cycles, basically, on partially finishing a request that then just times out. With ZGZ, we eliminate those pause times, and that means we also eliminated a lot of these IPC client errors. And I actually have a nice graph of that. So in this graph, graph shows the maximum GZ pass times. And we see that we have pretty frequent events of at least 1 second, sometimes shooting up to like 2 seconds. Where I draw this red box is when we switched from G1 to ZGZ. And the graph basically disappeared. Well, it didn't actually disappear, it just dropped to 0. So there's no pass times happening on garbage collection anymore. Well, that's expected because the whole point of ZGZ is that you don't have pass times. Like there's no stop the world pass times. But again, this comes at a trade-off because we spend more CPU time garbage collecting. So that's just the balance you have to find. So not necessarily better yet. However, if we also take the graph with IPC error rates, so this is basically how many errors happen on IPC calls, those also dropped. They didn't disappear because IPC errors can happen for many reasons, but they significantly dropped. That's the purple in this graph. So at the same time that we switch to ZGZ, lower pass times, less timeouts, less IPC errors. Now this is actually super significant because if we have less client errors happening, we have less retries, so it means less load on our cluster. It also means lower latency for consumers because we don't have to deal with extra latency costs by the retry. And the services can run a little bit more hot. So we can actually like raise the ceiling of how much CPU we can comfortably use without things getting really spiky. So this is all good news for us. We can just run our services faster. That's kind of what it comes down to. So we switch to generational ZGZ as the default. Okay, I've talked about virtual threads before, and I've mentioned all these times that virtual threads are one of the most interesting features in the JDK, in my opinion, that have been added for since many years. However, we kind of had a false start with JDK, was it 23 that got introduced, or 21? Because there was thread pinning still going on, and it meant that we would just get deadlocks on our services, and it was basically unsafe to use. It was safe for some use cases, it was not safe for us to use. So we basically had to roll back most of the virtual threads used at Netflix. That whole thread pinning issue is fixed in JDK 25, so now we start rolling out virtual threads again. Because that is fairly new, I actually don't have a lot of data on, oh, this is way faster or whatever the story is, because we just recently started looking at this again. What we can do is very easily add virtual threads to our frameworks. So we can add it to our Tomcat connectors in Spring. We can add it to our out-of-the-box thread pools that we use also in Spring. We can use it to our DGS data fetchers, and there's all stuff that happens in frameworks. So as a developer, you get the benefits from it, but you don't actually have to make any code changes. If we do want to use it in code, and that is kind of the next step that we want to get into, we kind of need structured concurrency, because without structured concurrency, there isn't really a nice way to leverage virtual threads, like from a programming perspective. However, if we use structured concurrency, we have to think about one more problem. This code example is like a typical code example for structured concurrency. And by the way, structured concurrency is still in preview, so this is not quite landed in the Java language yet, but it's in like the 6th preview now, so it's fairly safe to use. But this code is actually broken. It doesn't look broken, but it is. If we do a structured task scope.open and then do scope.fork, at the moment we fork, a new virtual thread is created. That's good. But it is a new thread. Most of the frameworks that we use, like Spring, Spring Security, Micrometer, they all store context on thread local. And that is how things have worked in the Java world for a very, very long time. These thread locals don't automatically get copied to a new thread. Now, this is not a new problem with virtual threads. This has always been a problem, and that is where the whole topic of context propagation comes in. But it's almost invisible in this case. So what would happen here is that these REST client calls would actually fail because there's no security context. There's also no tracing context, so you also have a hard time debugging this issue. And the issue sits right there. This open creates a new thread, doesn't do anything when it comes to copying thread locals around, and basically you're now in a broken state. So what do we do? Well, the issue is that all these frameworks that we've built on use thread local. And that is just how the whole Java ecosystem is built for all these years. In the Java language, together with context propagation, they also added scoped values. And scoped values from a clean technical perspective is a super nice ideal solution. But unfortunately, it doesn't really take care of the problem of migrating from thread locals to this new scoped value mechanism. There isn't really a nice bridge that would just work with all the existing frameworks and libraries. And that makes it really hard to adopt. And I still don't really have an answer to that, how we can adopt scoped values without rewriting a whole bunch of things deep down in our stack. But there is a nice workaround, and that is what I wanted to show here. When creating a structured task scope, so that is that open method at the bottom, if you don't give any parameters, you're basically in this problem that I just described. But you can actually give it a thread factory, and in the thread factory, you can take care of context propagation. So now you can fall back to one of the libraries that we have always relied on, like Micrometer context propagation. And by just a few method calls into that library, we can actually take care of the copying of the thread locals, and now our new virtual thread does have our context. This is not as efficient as scoped values, but it does work. So that is kind of this is the way how to start adopting context propagation, start adopting structured tasks without having to throw away all our existing libraries and frameworks. And there's one more JDK feature that we're super excited about, and that is Leiden. This is about AOT, and I'm actually not going to talk about that, because tomorrow Martine and Ian, two of my co-workers, they have a whole talk about this, how we are adopting this and what the infrastructure is that we've built around adopting this feature. So definitely come to their talk tomorrow, and they will tell you all about it. Go ahead. So the question is for different types of workloads, such as batch jobs. Is ZGZ also the best option? The answer is really you have to go and test and profile it. There is no generic answer for this. Very often with batch jobs, it is true that you don't care as much about the garbage collection, because by the time your job finishes, you might still have memory left. So why would you collect at all? And it might actually be cheaper to not do any garbage collection. So it really depends on the workload, and you really should test this. The reason that it works for most of our microservices is that it is like a really good fit for the trade-off between like the extra CPU time spent on garbage collection, but like lowering the errors. If you have more questions, let's do that at the end, because otherwise I'm gonna run out of time. A completely new area that we start working on is agentic workflows. And this is basically adding LLMs, adding GenAI to our Java services. So I'm not talking about adopting like the tools that help us write code. We're also doing that, but that is not Java specific. This is about putting GenAI in our microservices to make them smarter, more efficient in certain tasks, etc. And I'm talking here about agentic workflows. And this kind of comes from a blog post from Anthropic from quite a while, where they give an example of, okay, this is an agent and this is an agentic workflow. And for an agentic workflow, you're basically keeping control of the workflow. So we as a developer have more control. We figure out what the different steps are in a workflow. And we're just using LLMs in the parts where we want to add a GenAI functionality. And if you look at like the different types of agents in agentic workflows, there's kind of a scale here. And in the simplest case, we just add some chat completion, we just add an LLM to an existing Spring app. We still have our traditional GraphQL or gRPC API, we still have a database or whatever, and maybe for this one specific functionality, we want to do a call to an LLM, and we ask to build a summary or something like that. This is super simple, really nothing new. If we extend that a little bit, we are now mixing multiple LLM calls into a way more complex workflow. And maybe we even use an LLM as part of the routing of, okay, this is how we're going to use, or this is how we're going to actually process a request. So this is, for example, if we take natural text from a user as input, we can run an LLM and figure out, oh, this is this type of question versus this type of question, and route it to different parts of our source code. We might chain different LLMs, we might run different LLMs in parallel for different parts of the job. But the important part is that we're using all these different things, but we are still in control of the overall workflow. So we keep control of the agentic loop. The other important thing to realize here is that very often we are not chatting with this interface. We could, but we don't have to. Very often these are kind of services that still just have a GraphQL API, and this is something that we just trigger from like another system, or maybe it's a batch job that we want to run. But the important thing is that yes, we are adding multiple LLMs here, but we are in control of the workflow. And then finally, we have like agents that are more of a black box. This is your Cloud Code or your Codex or whatever agent you're using. And we are basically just talking to it. And the agent figures out, okay, to accomplish this task, I am going to do this thing, and this thing, and this thing, and then I'm going to ask the user again, and figuring it out, right? And all we do is give it MCP skills, file system, such things. But it is in control of figuring out what steps to take. Now, for these first two, especially the agentic workflow, this is where we actually build Java services and where we use Spring AI. And Spring AI really gives us all the functionality that we need to build such things. It gives us interaction with LLMs, we can do tool calls, we can do MCP. It's really the whole stack that we need to build these agentic workflows. And that is what we really start doing quite a lot now. And I want to kind of, just as a teaser, maybe kind of give an example of one of the services that we have built, focused on our developers internally. And this is a service that we built that focuses on the startup performance of our Spring apps. If you have really complex Spring code bases, at some point you're going to introduce a library that takes a lot of time during initialization. And now every time you run a test or you start your application during development, you're waiting for this thing. Now, a few years ago, we actually implemented the service, and basically it shows you the profiling data of, oh, this Spring Bean takes this many seconds during startup. Now, that's useful, but it wasn't very actionable for our developers, because the Spring Beans that you might be seeing in this list might actually come from a library that I'm not owning. So now I have to go find the source code of this library, I have to start reading the source code of this library, I have to figure out, okay, this is where the problem is, and then I have to think about, can I actually do better? So it's quite a lot of work to actually make this actionable. So what we did is we added an agentic workflow to this, and now in this same UI, we're actually just giving recommendations to our developers of, this is the problem, this is what you should do. So you get a summary that says, oh, there's some serious issues in certain Spring Beans going on, it takes a lot of time to initialize, it might be loading data, and we can actually click through. And it says exactly, okay, this particular class in this particular library is causing this problem. Maybe you should think about doing something more async. And now, as a developer, I actually have something actionable, and I can go and fix this code. And maybe in a future world, we actually have an agent fixing this code, right? But this just gives a lot of insights. And the way this is implemented is exactly what we saw on this slide just now, where basically in this agentic workflow, like we're connecting the fact that we already have this data in the database, this profiling data, but we now give that to an LLM and we ask it to analyze it. Now we ask, okay, go and find the source code for this library. Again, we analyze the source code with an LLM and we're tying all the pieces together. And that is really not hard to do based on Spring that we already have and Spring AI, and that is giving a lot of new possibilities for features to build. Now, since that we're talking about GenAI, how does Java fit into this new world of GenAI comparing to Python? Well, to be fair, maybe 2 years ago or so, Python was just a lot better at doing GenAI. Not because of the language, but because of the libraries that were developed in Python. There was just a lot more libraries available to do GenAI things than there was in Java. But since then, we have like fully caught up in Java, and we have frameworks like Spring AI and LangChain, and these libraries are better, or at least as good as what you can find in the Python ecosystem. And that means that from a library perspective, these things are really kind of the same. And by the way, I'm really talking about leveraging like GenAI, right? I'm talking about leveraging an LLM into our Java service in this case. I'm not talking about training models, that's a completely different world. I'm talking about leveraging existing models. So if the way you write these things is actually the same, it is really back to the old question. What platform are you most skilled in? You're all Java engineers, I'm assuming that is Java. And how fast does it need to run? We all know that Java runs a lot faster than Python does for like large-scale workloads. So it turns out that the JVM is actually a really good and important place to be when it comes to running these new types of applications. So I think we're in a pretty good spot with Java and the JVM. That's all the time I have on the second exactly. I can take a few questions.
Okay, you said gRPC is the default for all services. There is no bad job in the Netflix, like backend processing, you have to do a lot of, and then accumulate data where latency is not more important. Some timeouts is okay.
I mean, we do a lot of performance testing, and even though it's the default because it works for most services, for especially the larger services, there is going to be a lot of performance tuning and actually analyzing of is this actually the best choice or not. So it being the default doesn't mean it's the only option. It just means that for most services, this is what is out of the box the best choice.
Okay. Another question is, you last Spring Boot to Spring Boot 3, you used deterministic approach. Why this time Cloud A? Why not Cloud A plus deterministic plus AI?
Because it is actually really difficult to write things like open rewrite rules in a way that it takes care of all the different types of corner cases. And agents turn out to be much more flexible when it comes to these things, so, and also much lower cost for us to write.
I think cost could be a question because writing a recipe or something like that, deterministic way modify the code, could be much cheaper using AI. Like you can ask AI to, okay, find all the patterns and write the recipe for these patterns.
Yeah, we've experimented with that a little bit as well to basically let an agent write your open rewrite rules. That is a pretty interesting idea that we didn't end up going with because it seemed unnecessary. What we do though is we start with just prompts and then we find, okay, where is Claude spending a lot of time? Where does it do inefficient things? And for those inefficient things, we actually then let it, or we write scripts or programs to collect the data it needs or do the tasks that it needs, and then we plug that into Claude again. So it's not just prompts, it's like a combination of more deterministic things as well.
Yeah. Another question is regarding scoped or structured concurrency. I saw that you are using some wrapper approach. Why not use the Java agent to modify the thread pool executor and for joint task classes itself?
To use the what? Sorry?
A Java agent to modify the Java classes.
To use a Java agent. We've experimented with that a little bit. That is really difficult and really scary to get right.
So we did it for Uber and it is working perfectly.
I see. Okay. Let's talk about this further. All right, I think we're very much out of time. I think we should get out of here. Thank you.